Hello, welcome to Math 65, Pre-Algebra. My name is Dr. Jordan and I'll be your instructor for this course. I'm just going to go ahead and start with the good news. The good news is that the textbook is free online. Just go to openstacks.org, or I think you can go to openstacks.com if you forget, and it should be free. Pre-Algebra second edition. You can download it for free if you want to have a little PDF file on your desktop, or you can just view it on the internet for free. Or if you really insist or desire, you can order a copy. I think it's less than $40 to order it if you really do want a physical copy. Here's a quick little snapshot of what the website looks like. So you want the Pre-Algebra second edition, and I'll be following this book, section by section, chapter by chapter, so that you kind of know where I'm at. Although I don't require you to own a copy, I don't require you to do anything. It's just to know where we're at in the textbook and what we're doing in the course in general. Okay. This course starts with a review of basic math, and we'll pick up speed pretty quickly. So if you do find that you're getting kind of bored and you're wondering, when is he going to move on to something more interesting, it comes really quickly. One chapter I'll be doing stuff that, you think, really? Are we really doing this? And say, yeah, we're really doing this. And then the next thing you know, we're neck deep in algebra and geometry, and we're solving some more complicated problems. So this class has a tendency to pick up speed pretty quickly. Without any further ado, we'll begin with Chapter 1, Section 1.1, the Introduction to Whole Numbers. Not a lot of content in terms of complexity in this section. It's mostly vocabulary, learning the terminology, getting used to how I lecture and how I disperse the information, and then you get in there and do the homework assignment associated to 1.1. Okay, we actually start with what are called natural numbers, also known as counting numbers. These would be the numbers that your ancestors would have known, 10, 20,000 years ago. Human beings all around the world, no matter where they were from, all basically came up with the same basic idea. The symbols might have been different, 1, 2, 3, 4, etc., etc. You might have some more complicated ways of writing them, and some cultures write it like this. There's other ways of writing out the numbers. We use the Hindu-Arabic number system, which are typically used all around the world at this point. 1, 2, 3, 4, 5, 6. I obviously can't list every natural number out, so I'll just say etc., 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 etc. An important note is that 0 is not natural. All right, it's not a natural number. It's not a counting number. Okay. 0 is a whole number. Easy way to remember that. There's an O in whole. Yeah, whole number. Yeah. So the whole numbers start with 0. They include all the natural numbers. So the natural numbers are what we refer to as a subset of the whole numbers. Every natural number is in fact a whole number, but not every whole number is a natural number. Okay. We often draw these on a horizontal line called the number line. So let's go with example 1 and actually start doing some problems like you might see in the homework if you haven't had a chance to get to it yet. Although I did notice that many of you got ahead of me, it's okay. And you're already doing the homework, that's fine with me. You do it at any pace that you can keep up with. All right, graph the following points on the number line. I don't really have to say the word point, but. So let's say, I don't know, the natural numbers, also known as the counting numbers, that are at most 4, the whole numbers that are less than 6. Okay, so we have a number line. Yeah. Natural numbers, so we're going to start with 1. And then we're going to be very careful about words like at most. At most means less than or equal. Less than or equal to 4. So 1, 2, 3, and 4. So those would be the natural numbers that are at most 4. For the next one, whole numbers. So whole numbers start with 0. Whole numbers start with 0, and then we have 1, 2, 3, 4, 5, and 6. But we need to be careful. Less than means not including 6. So we are not going to put a dot at 6. Just 0, 1, 2, 3, 4, and 5. Okay, so I guess, you know, the words of the day here, or at least the introduction, example 1 is at most is less than or equal. Less means less than, but not including the number that's in question. So in this example, 6 is not being included. I'm not going to put a dot at 6. Now, one thing you probably learned, you know, when you're very young, is that when we write numbers, we write down a number, you know, 3 means 3, but 6 doesn't really mean 6. 6 actually means 60. The 3 does mean 3. The first digit on the farthest right digit, it's the only digit that's true. It means what it says it is. 8 doesn't really mean 8. 8 means 800. Yeah. 5 means 5,000. And 2 means 20,000. So this number is 25,863. All right. Notice what word is not here. And. Okay. We do not say 25,863. We just don't say it that way. There's a dash, or there's a comma, or there's a breath, a pause, but I don't want you saying and I certainly don't want you saying with. You just want to pause and write the next digit out. Okay. I'm going to be really picky about that kind of thing. You know, if we were in the classroom, I'd be walking around making sure that everybody is saying, reading, and writing it correctly. We often put commas to indicate groups of 3 so that we can separate them in our eyes. So this first number that I wrote down, let me just get rid of these circles because they're kind of in the way. This first digit that I wrote down is what's called the standard form. So if I say write the number in standard form, what I really mean is use the digits. Yeah. So each number represents a single digit. Okay. If I write it out like this, 20,000 plus 500, excuse me, 20,000 plus 5,000 plus 800 plus 60 plus 3. This is what's called expanded form. Yeah. And then finally, when I write it out in words, well, we just call that word form. So you have the way the number looks, what the number actually means, like mentally, how much quantity is actually there, and then you have the word form of the number. The expanded form gives us the place value. So the place value is what that digit represents. What's its value? How much is it really worth? So, you know, back a minute ago I said 6 doesn't really mean 6. Its place value is 60. Yeah. And so we always start with the ones all the way to the left, and then the tens. I don't know why I just said left. I'm looking at the camera backwards. The far right, and we read towards the left. That's what I meant to say. We start at the right and we read towards the left, the place value. So we have the ones, the tens, we have the hundreds, and then thousands, and so on and so forth. 10,000. I'm trying to write in these tiny little boxes. And so on and so forth as we go along. All right. Moving towards the left. So example 2. Write the digit for the given place value. All right, so tens. So what digit is in the tens? Tens would be 3. 3 would be in the tens place. Hundreds. 4. 4 would be in the hundreds place. $10,000. I'm skipping around a little bit. 10,000. So again, we have ones, tens, hundreds, thousands, 10,000. So 10,000s would be 9. And then as we move along, we'll go to the millions. Millions is 2. 2 is the digit that's in that place. I don't always ask for every place value, but you should know them all from right to left. We could keep going. Maybe I'll do another example with a much larger number And we'll see what happens there. Write the place value for the given digits. It's a 7, but it doesn't really matter. And then again, I should mention that these commas are not actually there. You know, sometimes we write them, sometimes we don't. It's become a relative standard in whole numbers to group them in groups of 3. Honestly, that's just so that your eyeballs can keep track of them. It's easier to count the place value. All right, so how about the digit 8? So the digit 8, what place is that in? So again, we have ones, tens, hundreds, 1,000, 10,000, 100,000, million. So this would be 10 millions. You don't really need the dash there. You can just say 10 millions like that. All right. How about 7? The digit 7. What place value is that in? Well, that one's the obvious one, right? That's the ones. It's the only one that really means what it says. 7 really means 7. Okay, one more. We'll go with 3. It's the place value for 3. So 1, 10, 100, thousands. And so that is the word form, or the basic reading of the word form of the number. Now we want to put it all together and we want to say the number correctly. Write the number in standard form. Write the number in standard form. So let's do a few of these, okay? I'll break this down. We'll get a whole bunch of these done here. So how about something like 25 billion? 25 billion. Or I could say 25 billion. So this is the word form, 25 billion. I want you to write it in standard form. In other words, use digits, 25 billion. So that is 9 zeros, 25 billion. You could also type it like this. As long as you can keep track of 9 zeros, the commas are not required. All right. I don't know about you, though. I find that when I have the commas, I'm more likely to have the grouping correctly. And if I leave off the commas, it sometimes causes a problem. All right, how about this? A little bit bigger now. 900 10 million 910 million 800 6,000. I have to move over here. 6,002. Okay. Again, we don't say 910 million and 806,002. We just don't say it that way. We say 910,806,002. All right, so 910 million. I know I just said it, didn't I? 910 million. 806,000. The dash is just telling me that I had to move over here. Some people put dashes between every pause. Other people just use commas. So 806,000. 806. There are no hundreds or tens, and then the unit is 2. Let's do another one of those. Those are one of the problems that I get a lot of mistakes on the quiz and the test, because students often come to me and they say, I get this comment a lot, Dr. Jordan, I'm really good at doing the math, but as soon as you do word problems, I get so confused. You're not the only one. That just makes you normal if you're like that. All right, let's try another one. 706 million. Again, I could put a comma or I could put a dash. $3,050. Okay, and again, this dash doesn't need to be here. It could just be a comma or a dash, or the word form is a little bit flexible in how you break it up with commas and dashes and things like that. All right, 706 million, 706 million. No 100,000s, no 10,000s, 3,000, so put a 3 in the thousands place. No hundreds, 5 tens, no ones. So you got to be careful for the missing digits and make sure that they're in the right place. I guess I have room for one more here while I move on to the next part. One thing I do is I vary how I do my separate parts. Sometimes I'll go A, B, C. Sometimes I'll do part 1, part 2, part 3, part 4. Sometimes I won't say anything at all. I'll just do a big problem with lots of different parts. All right, one more. This one I'm using dashes. And I hope I've made my point clear. Even without these dashes, this number would still mean the same thing. Okay. So 163,438. 163,438. Isn't it nice when there's no missing digits? When there's no missing digits, you can literally just read the numbers and write it down, and then put a comma if you want, or not. If you don't put the comma, it's still going to be correct. All right, we're starting to get into these large numbers. Next thing we're going to talk about is scale. So when we're talking about scale, we're typically talking about on a number line, although there are other applications of the concept of scale. When we're talking about small numbers, there really isn't too much to it. The scale is typically pretty obvious when you're close to 0, right? In fact, I could oftentimes, when I do some graphing, I might omit these numbers in between, right? And just say, okay, there's 0 and there's 5. And without really doing any math at all, other than just a little common sense, if I said, okay, what's this value here, you would immediately know that that's 6, right? Because you can clearly tell that each of these values is 1 unit. Yeah, that's a unit scale. It's a very common scale where we call these tick marks. Each tick mark represents 1 unit, so 1, 2, 3, 4, 5, 6. And as long as I stay relatively close to home, right, and I come over here and I say, okay, what's this point here? Since each tick mark represents 1 unit, you would clearly know that this represents 8, and this would be 6, and so on and so forth. It gets a little trickier as you get farther away from 0. Although I shouldn't scare you by saying it's actually complicated, but it's a little bit more complicated. There's a recipe that we need. Or a formula. In my class, I often refer to formulas and recipes in the same breath. So if I'm way out here on a number line and I say, this is, 510, and then this is 520, and you're farther away from 0, then we're going to need some sort of formula or some sort of recipe to determine where different values are on the number line. Okay? So let me formalize this procedure by giving you another example. So example 5. Find the values of A, B, and C. I'll use some letters on the number line. And I'll be a little bit more precise than that was just sort of a rough sketch. Let me be a little bit more precise here. So again, we're really far away from 0, so I won't even mark 0 on here. And I'll say, suppose this is 510. And suppose this is 520. And I want to know where is A, B, and I guess we'll do C. So find the values of A, B, and C. Notice I didn't put them all in alphabetical order. It's just to make you sort of pay attention to where you are on the number line. Okay, so here's the recipe. All right. The first thing you want to do is count the spaces between the given values. So I typically will give you 2 of the values on the number line, but I won't give you more than 2. So the 2 values that I give you, you're going to count the spaces. It's very important that you count the spaces and not the marks, not the tick marks. Don't count tick marks. Often called tick marks. Don't count those, all right? Count the actual spaces. So you have 1, 2, 3, 4, 5. Okay? The scale is equal to the difference in values divided by, here, let me use the old-fashioned divided by symbol, divided by the number of tick marks. excuse me, the number of spaces. I just said don't count the tick marks. So the scale is going to be the difference in these values here. Yeah. So 520 minus 510. So the difference is 10. Yeah, that's the difference between these values. Oftentimes, you'll just do that using mental math, right? You'll look at the two numbers. You'll calculate the difference. The difference between 520 and 510 is 10. Okay. Divided by the number of spaces. The number of spaces is there are 5 spaces. So 10 divided by 5, the scale is 2. So this is a 2-unit scale. That means that each space represents 2 units. Okay. So let's go back to the original question. Find the values of A, B, and C. So A is 510 minus 2. Yeah, so this is 2 units. So that'll be 508. That's the value of A. 2 units less than 510. All right. Okay. I guess I'll skip over here to B. B is 520 plus 2 plus another 2. So each one of these spaces represents 2 units. So that'll be 520 plus 4. So B is 524. That's the value of B. C is in the middle. So we actually have 2 ways to do C. You can do it by saying it's 510 plus 2, 4, 6. So plus 6. So that would be 516. If you go plus 2, plus 2. All right. Or if you're going to the left, you could do 520. Let me get rid of that. Minus 2, because you're going to the left, minus another 2, so that would be minus 4. You still get 516 either way. So find your given value, use that as a reference point, and then if you're moving to the right, you're going to add whatever the unit scale is. In this case, it's 2 units. It's a 2-unit scale. A 2-unit scale is really known as a fifth, right? You're dividing it by 5, but that's neither here nor there. Okay, so it's a scale of 2. Each space represents 2. Okay, and then I guess if I want to be absolutely clear about my answer, I would say A is 508. B is 524, and C is 516, just to make the answer clear. All right, so that's the recipe. To find a scale, whatever the unit scale is, you want to find the difference and then divide by the number of spaces. Let's do another example. Hopefully my camera will stay good. Let's see, example 6. Oh no, it's happening again. Well, maybe it'll come back while I'm writing it. Same question, find the values of A, B, and C. You might as well get used to this. This was the first video, and this happens quite a bit. I've tried turning off the autofocus, but this seems to happen quite a bit. Come on back. Sometimes it'll clear itself up while I'm writing the problem, so just bear with me here. So this one's going to be a little bit larger of a number line, a little bit farther away from 0. That's terrible. Can't even draw a straight line. All right, there we go. It doesn't really matter. Okay, so this one we're going to go out into the thousands. So this will be 18,500. And this will be 18,600. Okay, and then let's do backwards orders. Let's do A, B, and C. Hey, and look, it cleared up while we were waiting, so a little patience pays off here. Okay, so typically I'll give you 2 values. So the scale is the difference, 18,600 minus 18,500, divided by the number of spaces, 1, 2, 3, 4 spaces. So divided by 4 spaces. So it's the difference divided by the number of spaces. So the difference there, by the way, you don't really have to do that with a calculator or even writing it down. You can just do it in your head. 18,600 minus 18,500, the difference is 100. So this is a 25 unit scale. That means that each space represents 25 units. All right. We're not really saying what the units are. They could be feet, they could be meters, they could be miles, but in general, we just call them units. Yeah. Or in this case, we refer to them as natural or counting numbers. All right, I guess we'll do it in order. So we'll go over here, we'll do A first. A is plus 25 from 18,600, so that'll be 18,625. All right. B, again, you can either go minus if you go backwards. So that would be minus 25 minus 25. So B would be 18,600 minus 50. Yeah, subtracting 25 twice. So that would be 18,550. Yeah. Or you could have gone this way. Plus 25, starting at 18,500, and you still get 18,500 plus 50, which is the same value. So I actually recommend doing it both ways, because if you do it one way and you get one answer, and then you do it the other way and you get a different answer, it means you're doing something wrong. So you've got a confirmation check. You know that one's right. Okay. And then for C, we're going backwards. We're going to the left, so we're going to go minus 25, starting at 18,500. So C would be 18,475. And then to make my answers totally clear, I'd say A is 18,625. No commas are necessary. If you want to put a comma, you can, but I typically don't unless it's really emphasizing something important. B is 18,550, and C is 18,475. Okay. All right. Next, we're going to talk about rounding. Often round to a nearest place. We use what's called the 5 or greater rule. Okay, the 5 or greater rule. It really is just a matter of our humanity. You know, most human beings have 5 fingers, 5 digits. It's another name for a finger, a digit. You have 5 digits on each hand, and so we use the 5 or greater rule to decide whether to go up or whether to go down. Okay. Let's start with rounding to the nearest. Let's do tens. This one is going to have a part A, B, C. Okay, so round to the nearest 10. Now here's the deal with rounding. All right, and I deal with this, I want to just make this very clear now. It happens in all my classes, from pre-algebra all the way through all the different levels of algebra, all the way into trig, pre-calculus, and calculus. I still have to deal with the concept of rounding. So you want to go, look at the tens place, okay, and then look to the right. All right, this number is called the dictator. All right, the dictator dictates what's going to happen based on the 5 or greater rule. All right, they're the boss. They're the supreme fascist. All right. So if that number is greater than 5, then round the next number, the 9, up 1 unit. So if the dictator is 5 or greater, then round or add, I'm going to say add, it's a better way to say it, add 1 to its neighbor on the left. So whoever's directly to the left. All right, so we got 496. 6 is definitely greater than 5. Yeah, 6 is greater than 5. So I'm going to round the 9 up to a 10 and then replace the dictator with a 0. I'm getting so messy here. Let me just do it right underneath here. So 4, and then the 9 is going to become a 10, and then the 6 is going to become a 0. All right. Now remember, you can't have a 10 in this position. Right? That's the way numbers work. When you get to 9, the next place value goes up by a multiple of 10, or a power of 10, depending on where you're at. We're in the tens place, so it's just adding 10. So this really means 500. Yeah. So it's 4 plus 1, which is 5. And so the answer is 500. That was a really long-winded explanation. That was because I want you to have the recipe. Yeah, so this is the recipe, the dictator recipe. Now that you have this recipe down, we can go through these a lot faster now. Okay, round to the nearest 10. So here's my 10. My dictator is 2. The 2 is not less than 5. So if it's not greater than 5, I just said not less than 5. I think you know what I meant. It's not greater than 5. It is less than 5. greater than or equal to 5, then throw it away, replace it with a 0. So this number's gone. You're going to replace it with a 0, and so the answer is just 30. Now this one's tricky. This one's a little bit tricky. The tens place has an invisible 0 in front of it. So this problem says round to the nearest 10, but when I look at the tens place has a 0. Yeah. So it's all about the dictator. The dictator is a 4. 4 is not greater than or equal to 5. So we're going to round this down to a 0. It's going down to nothing because it's not greater than 5. Had that been a 5, I would have rounded up, and the answer would have been 10. All right, so now that you have the recipe, let's try some more. Round to the nearest 100. We'll just do 2 parts for this one. So round to the nearest 100. So we look at the 100 spot. Now here's the thing that I often get, and I'm not kidding. I get this at every level of mathematics. Students often learn this, when they're early in their math education, and then they just forget which way they're going. Am I looking left? Am I looking right? Or am I looking directly at that number? Real easy way to remember that is who made all the rules. Yeah. Right-handed people. I hate to break it to you left-handers out there, but right-handed people make up all these rules. So the rule is look to the right. That is the dictator. The dictator is always right. So the dictator is a 4. That is not bigger than 5. So that's going to become a 0, and then every other digit past that to the right becomes a 0. So this one becomes 54,800. So that going back to that recipe, when you replace something with a 0, you replace all the digits to the right with a 0. All right, here we're looking at the hundreds place, but we're not looking there. We're looking here to the right, the dictator. 6. 6 is definitely bigger than 5. So that's going to become a 0. This is going to become a 0. And then we're going to add 1 to the 5. So that's going to become a 6. So you get 7. I don't know if that 1 is big enough. So you're going to go plus 1 to the 5. And that's going to become a 6. Just a couple more. Example 9. Round to the nearest 1,000. Round to the nearest 1,000. So this doesn't have a thousands place, so that means there's an invisible 0 here. And I got no thousands. Yeah. So the dictator is the 5. Is 5 greater than or equal to 5? Yes. So we're going to add 1 to nothing. And then we're going to replace all of these digits with zeros. So 1 plus an invisible 0 is 1, and then followed by 3 zeros. And if you like, you can put a comma. If you don't need it, you don't need it. Oh, we're getting there. We're getting there. So where are we going to? Thousands. So we're going here, thousands, and the dictator is 7. 7 is, in fact, greater than 5, so we're going to add 1 to the 2, make all of these zeros, and we get 43,000. Not too bad, huh? You get the hang of it. You get the hang of it. When we remember these rules, I'm going to teach these now, but I'm going to come back and remind you of these when we start doing decimals, because when we start doing decimals, we'll have, 0.5293, and we'll have basically the same rule, but on the other side of the decimal point. We're right now in the whole number section. There are no decimals right now. So. Last example, example 10, round to the nearest 10,000. I really only need to do one of these. So we'll say 752,894. Just a one-part one to end this lesson off. Round to the nearest 10,000. So we'll practice our place value. Going back to the beginning, we have ones, tens, hundreds, thousands, 10,000s, so right here. And then we look to the right. The dictator is 2. Is 2 larger than 5 or equal to 5? No. So that gets turned into a 0, 0, 0, 0. And you do not round up. You do not add 1. So you will simply get 750,000. Okay. It was good to meet you, at least virtually. Come to my office hours if you have any questions on Zoom. Other than that, we're done with the introduction. I'll continue lecturing on the rest of Chapter 1 very soon. Until next time, this is Dr. Jordan. I will see you on the internet.